Hello, everyone. My name is Alec Kalingas. Thank you for joining us here this morning and for this Petrosys show on our volumetrics routines. We'll just be discussing a few things with our new slice-based volumes today in this webinar. And what we're going to be covering today, we're just going to be going through briefly our just some brief notes on our calculation method on grid-based slices and really some best practices and pitfalls, things that you don't want to fall into as far as traps and problems where you might be calculating erroneous volumes. And we'll finish the show with a small demonstration of the software. So first off, what is the Petrosys slice-based grid volumes? Basically, slice-based volumes are a way to calculate and report volumes as a function of depth and slice thickness. And in the end, you'll get a report. You're seeing a small fragment of an HTML report, which we'll discuss later on. But you can see that you're seeing volumes reported at 10-foot intervals going down through a couple of zones. And it just shows you how much volume is coming from which area in the zone of interest as a function of depth. All right. Another thing that slice-based volumes does, and this is a little bit more subtle, but we've introduced a concept of subcell prisms, and it's a benefit of grid-based slices over older methods because you can have low refinements or high refinements on the number of grid cell nodes in the subcells. As the subcells get larger and larger and increase, you'll get more and more accurate volumes. But each division of the subcells will slow down the volume calculations. As the subcells are decreased, however, results of previous runs with higher grid cell sizes, subgrid cell sizes, is retained, so that when you run additional volumes at more and more refined levels, it'll be a lot faster because you have the information from the previous run to define. Another benefit over the older method is the grid-based slices, which volumes it calculates over the grid cell prisms, is exactly the same as our color-filled display method. So basically, when you're looking at a color-filled display, if you see color displayed on your map in your grid area, you will definitely get volumes calculated in those areas. On a 2D map, if you see blank areas, which we'll discuss down further on in best practices, you won't get any volumes calculated over those areas. And that's true for the nonlinear interpolation that we use over the tops of the grid cell prisms. If you're looking at this map here, you can see the grid cells, and if we zoom in a little bit, you'll notice that inside of the grid cells, Petrosys doesn't linearly interpolate those prism tops. It's a third order polynomial that gets slapped down to the top of those prisms, and you can see that by the curvy linear nature of these contours that are being laced through those grid cells. And you should know, in the new method, in the new grid, the slice-based method, we use exactly the same interpolation method at the top of the prism as we do when we're color filling the grid. So it's a really important quality control measure to zoom in and inspect your grids and look at things before you run volumes. Whatever you see in color-filled mode will be exactly what you're going to be getting when you calculate volumes. And that's quite a big benefit over the older methods. Another benefit is new reporting features. In the old software routines, you only got text-based reports. You now have both text-based reports and much fancier HTML-style reporting. And as you'll see when we get into the demo, it's really creates an XML report in the background, and it comes out of the box with some XSLT processors that will create printer-friendly formats, HTML formats of the report. But you should know that if you guys are like XSLT processing, you can also write your own custom report forms to translate it to whatever view you want to see it in. And this is just more examples of some of the reports that are coming out. You'll notice you're getting those grid-based slices over here on the right, and graphics and everything, and you can still get the old text time report that you can use for cutting and pasting. Also in the reports, we're including a lot of metadata that we've never included before. I don't know if you know this, a lot of Petrosys users may, but as you play with grids in Petrosys, they're processed, they're run through grid processes arithmetic, we keep in the background a narrative of what's happened to that grid over its lifetime. And any grids that are used in a volumetrics run you'll get all of that metadata automatically dumped out to the report for you. And that's true for any of the surfaces, polygons, any of the input data that you use in the volumetrics run. You'll see lots of metadata in the report. Another big benefit is just our new interface. What you're seeing here is on the left side of the screen, you're seeing the older Petrosys Volumetrics interface. And you'll notice everything is packed into just one large panel. There's very few options for reports and that sort of thing. On the right, you're seeing the new slice-based methods interface, and it's just a lot more tidy. Everything's packed into one interface, split up and organized in various tabs. So it's just much easier to use for an end user. What kind of data can you work with inside of our volumetrics? Well, the typical sorts of things. You can run models with just a top surface and a single reference plane. You're allowed to have multiple reference planes, up to 4 of them if you'd like. You can have multiple surfaces, defining a top and a base, also with and without multiple reference planes. Of course, you can use thickness grids, isopachs as your input, and you can include bounding polygons to restrict the area laterally. When you use bounding polygons, the output report will show you, individual volume reports for each of the areas in question, as well as cumulative volumes for just the totals. Another thing you use for import is the volume calculator. You can use this to adjust the gross rock volumes that are going to be calculated by default, and you can use these little calculators to come up with conversion factors to try to come up with in-place hydrocarbons or recoverable volumes as well. So all those things can be used in input. Let's talk about some best practices, a little bit of training here. For Petrosys users, this is all verbatim. I can't speak to other volumetrics applications, but all of the things that we'll be discussing here definitely apply to Petrosys and probably can be used for volumetrics in general. In Petrosys, one of the things that we see quite a lot, don't let this be you, is grids that don't have the same spatial extent. What you're looking at here is a top grid and a base grid that don't match up. Now, when I say that they don't match up, we allow people to introduce and run grids that have different geometries. The grid cells can be different. You can even have rotated grids in our volumetrics. That's fine. What you don't want to have is 2 grids that don't cover the same lateral extent. So in this area, you can see these grids have quite a number of problems, actually. And if we look down a little bit more in detail, this area right here where you only have 1 grid, you will not get any volumes calculated in those areas no matter what you do, because that lower surface doesn't exist in those areas. It's just very, very important to inspect these grids before you run volumetrics. And you can use the 2D mapping tool to inspect them. You can put the grids displayed in the 3D viewer to inspect them. But it's very important to inspect grids for potential problems like this. You would not want to use this model to run volumetrics. In cross-section, it looks something like this, a little difficult to show in a PowerPoint, but it's very common for users to have a model like this, introduce a horizontal reference plane when they're creating the volumes, and they think that that horizontal reference plane will define missing portions of that lower grid, and that is untrue. In this situation, this small little area you can see here at the bottom edge of our model where you have the upper surface going beyond the extent of the lower surface, you will not get volumes there. So this is one of the main things that you want to look at before you even think about running volumes, is to display your grids. Use the 2D display, 3D viewer, whatever works for you, but make sure that these grids extend laterally far enough to take care of your situation. Another big problem that we see quite a lot are grids with holes. If you have grids that when they display on their 2D map, you're seeing blank areas. For instance, this is a very common user error. The user has created a structural map, and he's blanked the z-values inside of the fault polygons. We're going to discuss best practices on how to get those z-values filled in, but in short, you should never run volumes before you get all of these blank areas filled in, particularly over your fault wedge zones. again, if you don't see color filling on your 2D map, you will not get any volumes calculated over those areas. All right, so you don't want to see this before you calculate volumes. Clipping grids. This is probably the biggest user error that we see here out of the U.S. office, at least. It's very common for a person to have a situation like this. You can see they want to calculate the volume of interest. It's in yellow. That top black line represents my depth grid and cross-section, and I've got my oil-water contact. So it's very common if somebody wants to calculate volumes in this sort of a scenario, the first thing they are tempted to do is use our gridding and contouring package to clip the structure grid to their lowest contact, in this case oil-water contact. Right? Very, very common. Everybody wants to do this. This is definitely a don't let this be you. You don't want to clip your grids. In the mind's eye, once you've clipped the grid, you think you've got a structure that looks like what I'm showing here in cross-section. But you have to remember, a grid is not a continuous thing. A grid only lives at the grid nodes. There is no living of the grid in between the grid nodes. Nothing exists. So when you clip a grid, you've clipped out really vital portions of information. We can no longer extrapolate that grid through the oil-water contact because you've clipped out those nodes. And as a result, you've clipped out little bits of volume at the edges. It's an edge effect problem. All right? So these little areas in purple are showing you that you've clipped out that amount of volume. All right? So you've got your original depth grid. The red grid is shown, or the red clipped grid is just corrupted on the volumes. The solution to that is do not clip your grids. All right? Just stick with your original structure grid. Let the grid pass through the reference planes that you're interested in, be the oil-water contacts, the oil-gas contacts. The grids must extend through those contacts. If you allow the grid to extend through the contacts, the software itself will take care of these clipping problems down to the contact level. If you clip out those values, the grid values themselves, the software won't be able to extend those edges, and you're going to be missing volumes. So you do not want to clip grids. It's the most common user error that we see. I just can't stress that enough. Here's an example. We're just looking at an original grid, fairly pixelated, just to show you what I'm talking about. This is the result of clipping the grid, and you'll notice you've got a lot of really jagged edge effects going on, and that will definitely cause you to lose small amounts of volumes around that edge. All right? So you don't want to clip the grids. Again, if you clip the grid, it cannot extend those color-filled areas outside of that clipping value, so you don't want to do that. Looking at it this way, this is displaying the same information but simply using a reference plane, and you'll notice that all those really awful jagged edge effects are now gone. All right? Now this is true, letting the grids pass through reference planes, even if you're working with thickness grids. It sounds strange, but you really want your thicknesses to go into negative space. You want your thickness grids to pass through zero. Okay? Again, it's very common for somebody to have a thickness grid and think that they need to clip it to zero before they start running volumes. But you'll have the exact same problem at the edges if you do that. Right? You want those grids to extend into negative space so that we can interpolate at the edges and interpolate through the zero line. All right? If you don't do that, you will not be able to get volumes calculated around the edges. All right. Another best practice, gridding with faults. Now, for those of you guys that own the Petrosys software and use the software to run volumetrics, you might want to take some notes here. We covered this in the surface modeling course, the best thing to do with faults, but we're going to run through the practice very briefly in this short seminar. The issue here is getting the wedge zone included in your volumetrics. All right? And it's very easy to miss these small wedge zones. On the left here, you're seeing a color-filled display in the 2D map, and you'll notice that there's white, right? In the color-filled area, that means you're going to have missing volumes as well. If you have missing color flooding, well, by golly, you're going to have missing volumes. So you really want to watch this before you run volumes. Now, when you're Gridding with faults in Petrosys. The key note when you're going to create grid, you go to the faults tab, you introduce your fault file, everybody's familiar with that. But this little option in the lower left is very important, outlined in red here. Keep values inside of faults checkbox. It's a yes or a no. All right. That's what you're going to be using in a two-step process here to model your faults. So you really need to pay attention to that little checkbox. All right. The usual scenario, if somebody were just to grid a surface that had some faults and you kept values inside of faults, very commonly you'll end up with something that looks like this. Notice the slope in that fault plane. It's not a plane at all. It's a wibbly-wobbly surface. Doesn't look like a fault at all. Right? So another thing that you should do, when you're visually inspecting your data on the 2D map, look at the slopes. Look at things inside the fault wedges and make sure that they make geological sense, because that certainly does not. The preferred method, okay, for gridding faults in Petrosys is as follows. So you guys that use Petrosys and use our surface modeling tools, write this down. All right, step one. What you want to do is you want to grid your data. You're going to use your fault polygons, but you're not going to keep values inside of the faults. All right, so you're going to blank the values inside of the faults. And this is going to be your first pass. And after your first pass, when you display that grid on the map, you'll see something like this. All right, you'll see a good structure map, but you won't see any data inside of the fault zone. Step two, you're going to create grid again. But in step two, for your input data, you're going to use the grid from step one. Now, you may know this, you might not know this, but in Petrosys, if you use a grid as your input data, the output grid will be an exact copy of that input grid, and it will only grid nodes that are null. Okay? So in step two, the grid from step one is going to be regridded, but because we're using a grid as the input data, the output will be an unchanged grid where there was data, and it will just infill those areas that had null grid nodes. All right? So in step two, you're going to grid the grid, and the key is to use the linear gridding algorithm when you do step two. All right? You're not going to use minimum curvature. And when you do that, you're going to get a nice plane definition along that fault plane. So now if you look at the slope of that fault plane compared to the original one, I think you'll agree it's much more reasonable of a geological model. One final step in this fault gridding process, you're going to use grid processes arithmetic to merge those two grids. Okay, so you're going to merge the two grids together to come up with your final well-defined structural surface. Again, you're going to look at that in the 2D mapping application and the 3D visualizer to inspect your faults and make sure that you're not missing any grid values and you have nice planes specified along those faults. Okay, so that's the step 1, 2, and 3. Again, we cover that in the surface modeling course, but just briefly, those are the steps that we recommend that you take when you're trying to model faults inside of our software for volumetrics. Another best practice, before you do anything, again, I keep emphasizing this, you're going to want to inspect your grids. Now, you can see just by looking at this grid, there's some problems. Some of the faults don't have color filling going on. Now, that may or may not disrupt what you're trying to do, depending on if those areas are where you want to calculate volumes. In the 2D map, again, you're not going to be clipping grids, right? And you can use reference planes in the volumetrics, but you can also use minimum and maximum values in the 2D display. Here, we're displaying that color-filled grid with the lower contact 2020 so we can inspect that grid. All right? So use those reference plane values when you're displaying your 2D data. All right? And you can do it as for the minimum and the maximums. Notice in this display, once we've clipped off the max value, there's still a few areas where we're getting color flooding. You can see them in the sort of white island areas. Go to the next. You see these little areas that have been highlighted in red? You got to be careful. Those little areas, if you don't take care of them with bounding polygons and that sort of thing, they will creep into the volumes and give you too much volume. All right. So again, it's very important before you run volumetrics to inspect these grids on the 2D display. the 2D display color fill uses exactly the same interpolation as the volumetrics does, so whatever you see in color display, that's what you're going to be calculating volumes on. Also, you're going to be using the 3D viewer as well to inspect your surfaces, make sure that you don't have surfaces intersecting other surfaces, faults that are scissoring, all that kind of stuff you can look at in the 3D viewer. And also in the 3D viewer, you can use the same reference planes that you're planning on using in volumetrics to make sure that you don't have any extra bits of volume that you might be calculating or areas that just might not be covered at all. And then finally, in best practices, we alluded very briefly in the beginning of this discussion about grid cell refinement levels. And it's best to have higher grid cell refinement levels. It will slow the calculation down, but you will get more accurate volume reports and volume values. Again, as you run volumetrics, it will remember and use the results from previous runs, that might have had lower cell refinement values with the later runs to speed things up. All right. Okay. So we're just going to break here, give a live demo, just a very brief demonstration, going through a terrible lot, but a few things. And what we're looking at here is just a 2D map of a top surface calculated on here. And we're going to just sort of zoom in and around this map here. If I go to the full window, you can see I have two areas of interest defined here, outlined in red. Okay, those are the areas that we're going to be calculating volumes over. And I can use the 2D map to zoom down in here and inspect things. Now, got another bit of the display already set up, ready to go, where I'm using the reference planes when I've displayed the grid, so I'm only showing in green areas where we're going to be calculating volumes. And before you run volumes, you really want to just pan around, look at the grids, make sure that you don't have any blank values showing up. There's, everything is color flooding. Everything should look good before you start running volumes. All right. Also, the 3D display can be used for the same thing. Here you're looking at the same grid with that horizontal reference plane displayed. That's clipping off that grid. All right. And be creative. You can drape contours on top of the surface. You can drape cultural elements like section lines, your polygons, whatever you need to do. Just be creative to come up with a display that you can use to make sure that your models are okay. Now I've got my base surface and my top surface turned on this particular display now. But use the 3D modeler. Now you can see in this model I've definitely got some problems that I would want to normally take care of before I ran volumes. Okay, but use that 3D displayer to inspect your data and do some quality control on the surfaces and structures before you even think about running volumetrics. Now, back in the gridding and contouring module, which is where you actually calculate your volumes, I've got a pretty simple workflow here. It's just connecting to OpenWorks. It's calculating a couple of grids, a top and a base grid, and this step right here is running the volumetrics. Okay, so to get to that step, it's volumetrics grid-based slices. Okay, but I'm just going to double-click that task and discuss the interface very briefly. First off, on the Compute tab, this is where you can define your cell refinement levels. So if I start with a very low cell refinement level, it'll run fairly quickly. When I run volumes again and again and again, I can increase this value, and the subsequent runs will use the previous runs, and so it'll speed up the next runs as this value increases. Down below is where you define your units. Okay, you have to specify your grid vertical units. The horizontal unit you don't have to worry about. That will be picked up from the coordinate reference system of the grid. But you do need to pay attention to your vertical units. That's critical. And you have to pay attention to your output units as well. Okay. The Levels tab is where you're going to introduce these reference planes. This is where you do the reference planes. Again, you do not clip the grids to these reference planes. Those grids must pass through these reference planes before you run volumes, and these two surfaces do. All right? You can put in some little cosmetic things for the report and different line styles and things that you'll see in the report as well. I'm not going to discuss all these fancy colors. I think you'll get the idea when we start popping up some of the HTML reports, and you'll see what those do. But this area down below is where you can refine your volumes by scaling factor. You're allowed to introduce various things like porosity, oil volume factors and things like that. The interface will change whether you're talking about gas or oil. It's just a small calculator to help you come up with a small scale factor. The Polygons tab, this is where you introduce what polygons do you want to use to limit the lateral extent of your calculation. In this example, I've just got a couple of polygons that I'm using. Basically, it's just the north and south areas that I'm going to be calculating volumes over. Okay. The Reports tab, this is new. The Reports tab, you're definitely going to want to turn that on. And you can always get the standard text report that everybody's familiar with. That's pretty handy. It's just a text file you can use for nice, easy cutting and pasting out of and into other things. But the more important thing here down below is the new XML style reports. And this is where you turn on the fancy HTML report pages. You'll notice out of the box we come with several different style sheets for your HTML. Some are printer friendly, some are just good for web pages. But you should know that you can also create your own XSLT scripts to reformat these reports in any way that you see fit. All right, so these are just some out of the box reformatters. The charts and the chart axes, these are used to just cosmetically change what you see coming out in the reports. But let me just sort of run this really quick. We'll just crank that off, get that going. Okay, runs pretty quick, and this is what is calculated. So at the top here, you get totals for all zones across all polygons. All right, that's the lot. As you scroll down through the report, it'll start getting a little more detailed, start breaking the report up based on the different polygons. You'll get one of these blocks for each of the polygons in question. I had 2 polygons, so I'm getting 2 areas in the report for that. As you scroll down further, you just get more details on those areas. And now we're looking at the really detailed report area, both the 2 zones that I specified in the interface and the colors that identified them. And you get that both for each of the polygons. That's my north polygon. This is my southern polygon. Same information. As you go further down the report, you'll see all this metadata. So, for instance, it's included all of the information that the software has been tracking for that top grid, right, including a narrative for anything that the user's done. And Petrosys people might not realize this, but as you go to grid processes, arithmetic, and you add and subtract, you do things to a grid, you smooth it, and that kind of stuff, it's all recorded in the grid header. If you don't know that, you should know that. All those metadata details can be extremely valuable when you're, using these grids, and we include that data in these HTML reports. Again, you get some metadata on polygons that you used, units, and the contacts that you used in the report, right? And just a few other details at the bottom. So the new reports are a lot more robust than they ever used to be. If I just slide that over to the side, come back over to here, if we want to run another run and we want to get it a little more accurate, increase that to 5, the grid refinement levels. We'll let that guy run. This will take a little bit longer to run, but it's actually going to use the data from the previous run to help it in its calculation to speed it up. So you can see it's almost done here, and that wasn't too bad. So this is the new report. The data is actually almost the same. It's changed slightly, and you can rerun and rerun and rerun the reports over and over and over again to generate as much HTML as you like. Another note before we close out this webinar, these things you should know, Petrosys users should know that these things can be scripted and placed inside of a loop. And this report can be set to append mode. And that's really important because this workflow can get fairly involved. It could loop over and over and over and over and over again in a batch job with something changing slightly in the volumetrics. And all of those runs, if you set this to append mode, will just all be appended into the same report. So you can set up a big batch mode, run fairly complex volumetrics routine overnight, or maybe in batch, might take 30 minutes to run, but you can do that all with scripting, so it doesn't take any manual intervention. Okay, well, that covers pretty much everything that I wanted to discuss. So I would just like to thank you all for attending this short little webinar. If you have additional questions on Petrosys volumetrics, please contact your Petrosys support guy or gal, whoever they might be. We do have classes that are specifically oriented towards the geological modeling and volumetrics as well, where we discuss the best practices and a lot more detail how to model your fault planes, those sorts of things. So it's a very good class. So if you're interested in that, I really suggest that you give us a call and try to get into one of our volumes classes. But I'll close it at that. I just want to thank everybody very much for attending. Goodbye.